welcome the participants and especially the invited speakers. You all came here to exchange ideas and experiences related to the ecological sciences. The Ecological Integration Symposium is a place where students and visitors at Texas A&M come together and learn about topics at the forefront of the field and share their research through talks and poster presentations. This is the 18th sequential year that this symposium has been run by student organizers. They have also garnered advice and continuity from symposium advisors, Professors Lee Fitzgerald and Kurt Weinmiller. The organizing committee spent many hours putting this conference together, and I would like to recognize them up front. So organizing committee, please stand to be recognized. Thank you all for your hard work and effort. I'm sure this symposium will be a great success because of that. Today you will hear from 6 plenary speakers about their important work. Topics include Keystone individuals in spider societies, a periodic table of niches, sustainability in the Anthropocene, tropical forest regeneration, linking biodiversity, ecosystem function, ecosystem services and human well-being, and climate science and public policy. Tomorrow there will be 12 student oral presentations, sessions, and 1 poster session. The 12 sessions include topics as micro as genetics and animal behavior, and as macro as community ecology and ecosystem management. This year, the symposium theme is micro to macro, ecology in the Anthropocene. As you may know, the Anthropocene is the most recent geological time period and has been defined based on the overwhelming evidence that humans have significantly influenced Earth's systems. These include changes in atmospheric composition, geological deposition, erosion processes, hydrological processes, community composition, and species geographic distributions. Anatomically modern humans have been around for approximately 200,000 years. This is less than 1/10 of 1% of Earth's history. During this short time, we have seen a population grow to over 7 billion people. We have seen increasing rates of natural resource consumption, and we have seen more than 50% of modified land mass. The majority of land that has been modified by clearing fields, building cities, damming rivers, and removing mountaintops. These actions have stressed plant and animal populations, as well as other organismal populations around the world. Although major changes in the Earth's atmosphere, climate, and biotic composition have happened previously in our Earth's history, this time it is unique because one species is the cause. However, because we know that we are changing Earth's systems, we can determine what shape they take in the future. Let me close by wishing you all a wonderful 2 days of engagement during the 18th Ecological Integration Symposium. Thank you.
Thank you so much, Dr. Wine, for that introduction. And thank you again for everyone being here. I'm pleased to introduce our first plenary speaker of this year's Ecological Integration Symposium, Dr. Jonathan Pruitt. Dr. Pruitt got his graduate degree at the University of Tennessee, Knoxville. He was then a postdoc at the Center for Population Biology at the University of California, Davis. Dr. Pruitt is currently an assistant professor in the Department of Ecology, Evolution, and Marine Biology at the University of California, Santa Barbara. Dr. Pruitt researches a broad variety of social and non-social systems, focusing on how an individual's personality influences the ecology of individuals, groups, populations, and communities. Being an entomologist myself, I was excited to see that he studies social spiders, paper wasps, and slave-making ants, but he's also researched systems such as old field communities, and in mid-tidal invertebrates. Dr. Pruitt has numerous highly cited papers appearing in journals such as Proceedings of the Royal Society of Biological Sciences, Nature, Ecology, Animal Behavior, and American Naturalist. Dr. Pruitt has also received many awards for his research, with just 2 examples being the Outstanding New Investigator Award by the Animal Behavior Society and the 2015 Elton Award by the Journal of Animal Ecology. And Dr. Pruitt is also an incredible communicator of science. He's been invited to give talks all around the country, which was part of the reason that we'd heard about him. Heard that he was just this amazing speaker. So very excited. And additionally, on RateMyProfessors.com, which is a very reliable source, he's gotten outstanding reviews from all of his students, every single one of them, which is a pretty impressive feat. Students went so far as to say he was the best professor that they've ever had, lauding his interesting and always entertaining lectures. So today, Dr. Pruitt will be speaking with us about Keystone individuals and spider societies, pros and cons. So please join me in giving a warm welcome to Dr. Pruitt.
All right. Oh, I have it. Oh, yeah, great, cool. So, first of all, thanks for having me. Thanks for showing up super early, and thanks for setting the bar so high on what I'm supposed to be doing today. And I'm really excited to be the opening act for a series of fantastic scientists that cover a broad range of disciplines and various scales. And I'm going to talk to you today about organismal biology and social spiders, and I will at times at least try to weave a narrative that involves humans and human societies, and so that is intentional, one that is transpiring. So thanks for having me, and I'll try not to disappoint you. All right, so what maintains diversity? Pretty much all of ecology and evolutionary biology is to some degree preoccupied with diversity. And so maybe you're interested in what allows different phenotypes and reproductive strategies to persist in a single population, like in these lizards here, or maybe you're interested in these beetles that have different subpopulations that maintain independent evolutionary trajectories in the face of gene flow. Is that interesting? Or maybe you're a community ecologist or ecosystem ecologist working in neotropical rainforests or Indo-Pacific reefs, and you're interested in what allows all these species to occur in just one area with finite resources. Wow. And then there's the alternative view, and that is, like, who cares, right? What does a phenotypically diverse population of lizards do that's special that a phenotypically monotypic population couldn't do? Or what does a, evolutionarily diverse metapopulation of beetles really do? Or why is it that we care about these species-rich hotspots? Why are they functionally significant? But I address these questions not in terms of species differences, not in terms of differences among subpopulations, but I explore the ecological consequences of biodiversity at the level of the individual in one key functional trait, and that is behavior. So I study temporally consistent individual differences in behavior, aka animal personality. So maybe that makes you blanch for a moment. Let's have a little moment here, what I actually mean by that. How many of you have ever, I'm not going to call on you, so don't worry about raising your hand, but how many of you have ever had a dog? Raise your hand. Or know what a dog is, or have seen a dog before. Exactly. All right, so if you were, say, I don't know, a corgi enthusiast, and you had a litter of corgis in your home that you spent all day long with, you would come to know these corgis quite well. You would say that some of these corgis behave differently than others. They have little personalities that you're familiar with. Some are more active, some are more aggressive, some are more gluttonous, some are more frenetic, whatever. You would say that they have these little personality types because you're familiar with them. These individual differences in behavior manifest in human populations. I have a characteristic way that I behave, and vice versa for you. But these individual differences don't just manifest in human populations, they don't just manifest in domestic populations, but they occur all over the animal kingdom, and they have large consequences for how individuals live their lives. Right? So just for an example right here, let's talk about these funnel web spiders right here, where female spiders differ in their level of aggressiveness. Generally speaking, when you're a funnel web spider, it's good to be an aggressive female. More aggressive females capture better territories, they get more food, they reach a larger body size, they have larger egg cases. So why is the world not overrun with wantonly aggressive female funnel web spiders? Well, the problem is that these same females that have the best territories, the largest egg cases, the largest body sizes, also suffer from a maladaptively high incidence of precopulatory sexual cannibalism. What that means is the same females that seem to have the most reproductive potential end up killing all of their would-be suitors and dying virgin spinster spiders effectively sterilized by their very high levels of aggressiveness. And this is one of the characteristic phenotypes of a personality, is that you just can't turn it off when it's advantageous. That your personality is with you all the time, and that it could cause all sorts of performance consequences. And so I studied this sort of phenomenon in the context of a social organism. So I addressed questions like, how do individual workers or group members inside of a society differ in their personality types along one or more axes of behavior? How do the mixture of these types of individuals, these types of personality types, beget differences among colonies and their collective phenotypes to cause more aggressive or less aggressive societies? And to what degree do societal differences influence their success? And this is really important because I try to phenotypically engineer societies that will either flourish and produce tons of offspring societies or wither and die as a consequence of their organizational traits, with animal personality being the underpinning phenotype. And just to highlight for a moment, the consequences are vast, right? So for my social spiders, between 60 and 90% of colonies go extinct every single year. Every single spider within the society dies. Nobody escapes. Death, death, death. Little spider carcasses blowing in the wind. And so there are enormous consequences for getting it wrong. You and all of your sister cousins are going to die together. So I study social spiders. Yeah. And so this is the portion of the talk where I ask you, how many of you even knew before today that social spiders, well, or before you saw my talk or whatever, that social spiders were a thing on planet Earth? Raise your hand. Maybe like 40% of you. And you know, you're not a random subset of the population. Most people, most normal people, don't actually know that social spiders exist on planet Earth. That's because out of the 47 or 48,000 species of described spider on planet Earth, about 25 are social. The numerator, that 25 number, that's not changing. And there are probably many, many more species of other species of spider that have yet to be described. So it's not happening all the time. But unless you find yourself traipsing around lowland East Ecuador or Andhra Pradesh, southern India, or Madagascar, or wherever, you're likely to encounter these things in your backyard. It's a rare phenomenon. So because sociality is so rare in spiders, we're going to talk briefly about what it is to be a social spider. So first, we're going to talk about colonial spiders, depicted on the left here, an example of Certophora from Renilophauna, Madagascar. And so colonial spiders are a little more abundant. There may be 100 species of colonial spiders. They make these giant webs together, like on this tree here. But inside that web, there are little subwebs that are about maybe the size like a fist. Maybe you can see them here. And each of those subwebs is occupied by just one female spider. And she defends this territory from intrusion by conspecifics. So if another group member moves into her territory to, say, steal prey or something, they'll interact aggressively and perhaps injure or kill one another. So they have very few affiliative interactions. However, if you're in a social spider, like this is Stegodactylus saracenorum in Andhra Pradesh, southern India, these individuals cuddle up against each other. So in this giant web here, you'll see these sort of fist-sized nests. And within each of those nests, between 50 and 2,000 individual social spiders basically cuddling up next to each other. And they're non-territorial, so individuals are nestled right up against each other, and they'll move between these sub-nests without any problem there. And they also engage in a variety of cooperative tasks, which we'll talk about in just a moment. Alright, so social spiders 101. Every single spider I'm going to talk about today is a boy spider. It's a male spider. And that's because social spiders have a highly female biased primary sex ratio. So that's because there are 9 or 10 times as many female embryos as male embryos. And females are the movers and shakers within the society. They cooperate in a variety of tasks. They make these giant webs together that are so charismatic. They capture prey together like a pride of lions. So like the individual spiders might be maybe, I don't know, a centimeter long, but they can subdue morpho butterflies or lumber grasshoppers or even small vertebrates. We find carcasses of small mammals in their webs. But probably the most captivating thing of all is that they actually engage in suicidal alloparental care. So these females capture prey for their young. They, like all spiders, regurgitate the contents of their stomach to liquefy their prey. They slurp up that vomit and prey, and then they regurgitate that into the mouths of their offspring, like a mommy bird would, or something like that. However, just before these females die, the last thing that they ever give their offspring is a final meal by liquefying their own body by a programmed cell death, and then being ripped apart by their offspring, matrophagy or gerontophagy, the eating of your elders or the eating of your mother. And that's actually been demonstrated not too long ago that when females are regurgitating the contents of their stomach to their offspring way before, that decomposition process has already started. So they're actually vomiting up the contents of their own viscera while feeding their offspring. So, how about that? Alright, so it's clear that these are foraging societies. These are foraging societies, so it's the ability to subdue larger and more profitable prey that begins the evolution of sociality in these animals. And these organisms are highly inbred. So new colonies are founded when pre-impregnated females found their own colony. The colony grows by offspring breeding brother to sister, and then and there's no mixing across society. So they have relatedness coefficients between 0.7 and 0.9, very nearly clonal in some species. I studied the desert social spider in southwest Africa, Stegodactylus demicola, which is native to the Kalahari and Namib deserts and adjacent savanna habitats. And individuals in the species differ in their boldness, which is just described as individuals' tendency to put themselves in a risky situation. Individuals that are bold one day tend to be bold in subsequent days and the rest of their lives, in fact. And individuals that are shy one day tend to be shy for the rest of their lives, so this has a relatively high level of repeatability. Within these societies, the single best predictor of how a whole society behaves is the boldness of the single boldest member of the group. The individual with the most extreme personality type within these groups is the best predictor of how a colony in aggregate is going to behave. If you just add one extremely bold individual, it changes the collective behavior of a society. You remove those bold individuals, and it goes back to normal. So adding just one extremely bold member to a group of other member of society to an otherwise shy society increases the number of attackers that respond to prey by 400%, and increases the number of individuals that come out to build their web each night by 250%, and it actually, under stable conditions, improves the performance of the whole society. These societies that contain one extreme phenotype individual, at least in laboratory, gain twice as much mass. So these little extreme phenotype individuals actually cause the rise and proliferation and success of these societies. And when they're absent, it's costly for the society's performance. And just for a moment here, I'll say that these bold individuals, these extreme phenotype individuals, are actually elites for their colony for a short time after colony establishment. So if you establish a new colony experimentally, or fragment one, at least for a little while after establishment, the boldest member of the group is the one that does the majority of the colony maintenance tasks. After a few days, its involvement tapers off, but its social influence persists after this time. How do you determine how bold a spider is? You can't give it a personality test. In this case, you can't self-report. So we put it into a standardized behavioral assay where we take a spider, we put it into a box, and we let it wander around for a second for a 30 seconds acclimation period, and then we puff it with an infant nose cleaning bulb, which these spiders can't see all that well, so all they detect is a giant puff of air coming towards them, and this frightens these spiders, and it causes them to engage in a death feint, where they pull on their legs, and they death feint for a variable amount of time. Now, some individuals are in this death feint for just a few seconds, and they pop right back out. Mind you, these are not visual animals. They have no idea, if this was a bird, they have no idea whether it's still there or not. And so they just continue to go back to their normal activity, hiding for just a moment. However, shy, fearful individuals will engage in this death feint, and then knock them out of it for 10 minutes, 20 minutes, half an hour. Presumably because they have no sense of whether or not that predator is still around. And these individual differences are highly repeatable, and they're associated with the tasks these individuals perform in the society, and the level of social influence that they exhibit. So Stegodactylus demicola has developed, at least in our laboratory, and it's actually now taking off in the literature, thank God, it took long enough, as a model for Keystone individuals, where I'll get into this, what precisely I mean by Keystone individuals just now. So by Keystone individuals, I am referring to a kind of individual that, because of its presence, it exhibits a disproportionately large influence over the collective behavior and success of its society. So you might say, how often could that possibly happen? But a recent review of this, it's not that recent, it's 3 years old now, showed that there are more than 86 examples of this in the literature. So maybe you'll have knowledgeable matriarchs inside of elephant societies, or tutors inside of bird societies that have large social influences. And they're advantageous. And they're a general phenomenon. We found them from microbes to various kinds of invertebrates, up to cetaceans and elephants. So lots of different kinds of taxa have these socially influential individuals. They have wide-ranging effects. Keystone individual makes it sound like it's a good thing to have a Keystone individual around. And if you're talking about a knowledgeable matriarch or a tutor, in fact, it is advantageous for these individuals to be around. But equally as often, or perhaps not quite as equally as often, but fairly regularly, these key individuals actually have really, really bad effects. Right? So super spreaders and disease transmission dynamics are a kind of Keystone individual, but they have a bad effect because they're responsible for all these secondary transmission events, and they can result in the collapse of a society. Or if you're talking about water striders, which spend about, I don't know, if they have their way about 60% of their day in copula, the males basically skate around on the water surface waiting for females that are not currently copulating, skate over the female, and initiate copulation. However, some of these males are much more aggressive than others. We term them hyper-aggressive males that are so zealous, so frenetic, so whatever, that they basically copulate with everything. They try to copulate with food, they try to copulate with other males, they try to approach females from directions and angles that are impossible to copulate, and so these hyper-aggressive males actually scare all of the female water striders off of the water. And so that's all that's left on top of the water are a bunch of males, not in copula. And so one hyper-aggressive male inside of these societies can basically sterilize the copulatory swarm for all the other males. So sometimes not such a good thing to have a keystone around. Sometimes they're bad. And possibly the coolest thing to me is that the very same individuals that can help your society under one set of circumstances can ruin you during others. So it might be great to have a tutor or a matriarch until it gets a disease, right? Or until it has bad information or something, it becomes compromised in some way, and that in turn can become a major point of susceptibility for your society. So they become some sort of like fulcrum for the performance of the group. So, are keystone individuals a bad idea? So if we just assume for a moment that most keystone individuals, on average, during most days have a positive effect, I still think that they might not be a very good thing to have around. Because if you're relying on this keystone individual for the performance of your group, what do you do if it just leaves you? Or it just dies? What are you going to do? What are you going to do? The keystone is gone, right? So you shouldn't rely on these things. Or what if these individuals are reservoirs, living archives of information like matriarchs and elephant societies, or tutors and birds? What if they're incompetent, right? What if they have bad information? Could they proliferate that? Or what if you have an enemy? What if you have a parasite or a disease or a social parasite or a heterospecific that can manipulate the behavior of these key individuals? Could this turn out to be a sort of a switch by which you can manipulate the behavior of the whole group? Seems like a disastrous idea. And so that's actually what we're going to walk through today. These various bad things that can happen to keystones and see what happens. We're actually not going to talk about this last thing today. That's actually all my graduate students' work who's here, but I don't think he's actually presenting. But I'll mention him again later on. But if you're interested in this last topic, you should go over to Rice University where Nick Kaiser is working, doing great work on that topic. But we'll talk about the first two today. All right, so what happens if this keystone just dies, it disappears, it's no longer here for you? What's going to happen? So the prediction is that the effects of keystone individuals could linger after they're gone. So there could be some sort of legacy effect, right? So if they vanish, maybe at least for a little while, we'll be able to detect their social influence after they disappear. And then secondarily, these legacy effects, these echoing effects after their departure, should scale to how long these keystones were in the group to begin with. The longer that a keystone individual has to influence the group, the longer we anticipate their legacy effects to persist after they're gone. And if they have a relatively short tenure, presumably these legacy effects should be quite short. So to evaluate this, I established experimental colonies, which start on day -20, which will make sense in just a moment. All right, so we have 19 individuals that we put in together on day -20, 19 shy individuals. Then to these colonies, we add one extremely bold individual of varying levels of boldness. Sometimes it's slightly bolder than everybody else, sometimes it's way bolder than everybody else. And we add those individuals either on day -20, day -10, or day -5. And then on day 0, we remove those keystone individuals, so they're no longer present within the society. And then we see, after they're gone, how long do their effects persist? And so then we look at the collective behavior of the society, how many attackers attacked prey on day 1, 3, 6, 12, and 24 after the keystone's departure. And at day 24, we should know that at this point, the keystone has been gone longer than it was ever in the colony. So 24 days it's been gone, it was only in the colony for 20 days to begin with. And then for our controls, on day -20, we have 18 shy individuals and 1 bold individual, and then we just add some generic shy Joe Schmo on day -20, day -10, or day -5, and then we remove those shy generic individuals on day 0, just to control for the fact that we're manipulating group size. So this is something special about adding and removing these bold individuals, and not just some generic individual. All right, so we're going to look at the days since removal along the x-axis here. We're going to look at the days since the keystone was removed on the left-hand panel, and days since the generic was removed on the right-hand panel. The situations where keystones were only in there for 5 days in white, keystones were in there for 10 days in gray, and then in the cases where keystones were in there for 20 days in black. The y-axis here is the correlation coefficient between the boldness of the single boldest member of the group and the number of attackers. How tight is that link between the personality of this extreme phenotype individual and the number of attackers that respond to the group? If that correlation coefficient is high, If that correlation coefficient is high, that means that there's still a tight association between the personality type of these extreme phenotypic individuals and the collective behavior of the society. If that correlation coefficient drops to 0, though, that means that there's no longer a link between the phenotype of this extreme individual and the collective behavior of the group, which means no longer can we detect an effect of these socially influential individuals. So here's the data. So for all of these treatment groups, for days 1 and 4, regardless of whether or not the Keystone individual is in there for 1 day, or 1 day, or 5 days, or 20 days, it doesn't matter. There's still a tight association between that Keystone's behavior and the collective behavior of the group, which means, at least for a little while, all of these societies have a legacy effect. We can still detect an effect of these Keystone individuals after their departure. However, by day 12 or 24 here, we see that for cases where the Keystone was only in there for 5 days or 10 days, we can no longer detect an association, an effect of these key individuals on the collective behavior of the society. And if you just add or remove generic individuals, that Keystone is still there the whole time, and so, not shockingly, there's still a tight association between the behavior of these key individuals and the collective behavior of the group. And what this means is that if you're a social group and your key individual is just departs or is murdered, after they're gone, they still have an effect on the collective behavior of the society. Their social influences echo through time after their departure, and those echoes persist in a way that scales to the Keystone's tenure within the group to begin with. A long persisting Keystone individual has legacy effects that persist for a long period of time, and a Keystone individual that's only there for a few days, those effects vanish quite quickly. So, what happens after a Keystone's disappearance? Well, I have good news for you. Their effects can persist. So if they're actually advantageous, then their positive effects on group performance could persist after their departure. And secondarily, these effects scale to how long these individuals were in the group to begin with. And that's good, right? So a long-lasting Keystone individual can beget a positive influence on its society, and those positive influences can persist after its departure, long after its departure, even beyond its original tenure within the group. So what happens if your Keystone's misinformed? What happens if it's incompetent? What happens if it holds bad information? And if you remember what I talked about before, I mentioned that these Keystone individuals are elite individuals for a little while after colony establishment. So after the environment changes, all of these shy members of the group basically decrease their involvement in all colony maintenance tasks and just hide within the colony's nests. And then these extreme phenotypic individuals come out and start capturing prey and rebuilding the colony and things like that. And so, after the environment changes, the first individuals to acquire new information about their environment are these key individuals. So they determine what the level of risk of predation might be, what the level of food availability, and what's out there in the world. And so my question here is, what happens if that information that they glean is accurate or inaccurate? And so the prediction here is that both good and bad information will have their largest consequences in the hands of a Keystone individual. So if a Keystone individual has good information, then it should help the society soar. And if a Keystone individual has bad information, it should make the society wither and die. And so when we want to see, we predict these effects should be larger when the information is in the hands of a Keystone, rather than just some generic shy Joe Schmo. Alright, so for this, how do you actually give a spider bad information? Well, what you do is you have to train them, right? So I train individual spiders that are either Keystones, gold individuals, or generics, just some shy Joe Schmo, and then I train them to associate one of two novel vibratory stimuli, vibration A, with a predator. And then one of two novel vibratory stimuli, vibration B, with a predator, right? So I consistently pair one of two novel vibratory stimuli with a reward towards the colony's most dangerous predator, a predatory ant. And then in some individuals, I actually reverse this, where vibration B is consistently paired with a prey item, and vibration A is consistently associated with a predator, right? So I'm training them to associate novel stimuli with rewarding and aversive outcomes. And then I have control individuals, which have experienced an identical number of vibrations, A and B, but they're not consistently paired. So sometimes vibration A means food, sometimes vibration A means predators, but they have an identical number of encounters with the two vibrations, and with the outcomes, there's just no consistent pairing. This is a yoke control in animal behavior and learning studies. So I then create experimental societies of 9 naive spiders and 1 trained spider. And then I detect how long it takes the whole society to learn as a group that vibration A is food or a predator, and vice versa for the opposing stimuli. Right? And then, just to be able to create situations where the Keystone individual has accurate or inaccurate information, I then subject colonies to situations that either match the training of those trained individuals, so they hold accurate information, or I reverse the association for the whole colony. So the training of those focal individuals is now inaccurate. And then I suss out what the effects are on the collective learning of a society based on whether these individuals have good information or bad information, and whether they're generic individuals or keystone individuals. And so what do you do to reward a spider? Well, when the spider comes out to attack the rewarding stimulus, I give it a fragment of a cowering moth, which is just one of the most abundant predators in nature. If I want the spider to learn to avoid a particular stimulus, I pair the stimulus with a pugnacious ant and a Blepus custodians. This is a really voracious predator of my spiders that can, when they detect a colony of spiders, can dismantle the entire colony, hack up all the group members, and carry them away on foraging trails in just a few hours. First time I ever encountered this ant, it actually captured all of my colonies that I set out in one single day. It took about 3 weeks to set up all those colonies, and they were just murdered in a number of hours. No, not everything works out dandy. Alright. So the question is, can I train spiders? So we're going to look at learning curves here, the latency to attack along the y-axis, and the trial number along the x-axis for keystone individuals, which will be in light bright color in green, dark green color will be generic individuals, and controls will be in gray. And so we're just going to look at how long these individuals took to attack this novel vibratory stimulus across iterative trials when it was paired with a rewarding outcome, when it was consistently paired with cowering moth. And so regardless of whether stimulus A was paired with cowering moth or stimulus B, the latency to attack over time goes down. And that means that these spiders are attacking this novel vibratory stimulus more and more quickly, presumably because they've learned that this novel vibratory stimulus means food, right? Cool. And then if I pair these novel vibratory stimuli with their most dangerous predator, the latency to attack goes up. They become more and more reticent to attack the animal that's very likely to murder them, right? And if you remove all those controls, it becomes a little clearer that, in fact, the latency attack goes down, the latency attack goes up, based on whether or not the vibratory stimulus is paired with a prey item or a predator. So that's cool. I can train individual spiders. That's a necessary precondition for this study. But now what happens when you throw these spiders into a group of naive individuals? Can one informed individual, generic or not, change the collective behavior of society, the rate with which the whole society learns about their new environment? So we're going to look at informed individuals in the left-hand panels and misinformed individuals in the right-hand panels. Keystones will be in this bright pink here, and informed generic individuals will be in this red, and controls will just be in this lame gray color. And then along the x-axis we'll have the trial number, and along the y-axis we have the latency to attack of the whole group. And we're looking at situations where these vibratory stimuli are paired with a rewarding outcome, with the cowering moth. And so, if you have an informed individual, regardless of whether it's an informed generic in red or an informed keystone in pink, the latency to attack for these societies is lower than control colonies by about half of the study. So yes, having one individual harboring accurate information, regardless of whether it's a keystone or not, basically increases the rate with which the whole society learns to attack a novel, profitable vibratory stimulus. That's good. But this is actually at odds with our hypothesis. It's not any better to have good information in the hands of these key individuals. As long as somebody has good information, it's good. What happens if it's bad information? Well, different story. So there's no significant difference between control colonies and colonies that have a misinformed generic Joe Schmo. They have an equivalent latency to attack across these trials. However, if you have a misinformed keystone individual, your most socially influential member of your population has bad information, well, the whole society has longer latencies to attack throughout this entire trial, which means that these societies are taking longer to learn that this novel resource is available to them. They're avoiding it for long periods of time. This is missed opportunities for foraging, right? If you take forever to attack a prey item in the wild, guess what happens? It gets away, right? So it's very costly. And in these trials, the prey items could get away. So we'll figure out whether or not there's a cost to this in just a moment. What about the dangerous stimulus? So again, the informed colonies will be in the left-hand panels, the misinformed colonies will be in the right-hand panels, same axis as before, same color scheme as before. Well, it turns out if you have an informed generic or an informed keystone individual, doesn't matter. Colonies are really, really good at learning that this new novel vibratory stimulus is your most dangerous predator, and that you should avoid it. So accurate information, no effect at all. It doesn't matter whether it's in the hands of a keystone individual or a generic. However, if you give misinformation, different story. Turns out, well, there's no significant difference between misinformation in the hands of some generic and the controls, but if you have misinformation in the hands of your most socially influential individuals, for a short period of time early on in these trials, these colonies are rushing out to attack their most dangerous predator, probably to get themselves murdered by the ant. We don't actually allow the ants in this situation to murder our spiders, but presumably the cost will be quite large. So although it's a short-term effect here, it's only for a small number of trials, you only have to mess it up one time for these ants to kill you. So Presumably the costs are quite large. So misinformation in the hands of your socially influential individuals? Bad news. Some generic? Who cares? So are there any fitness consequences to that information? So we actually don't know what would happen if we allowed the ants to attack our spiders. We trained these spiders, and so we don't want them to get murdered. Right? However, we did mask them to begin with, and mask them at the end of the trials to see how much that changed over the duration of the trial. And so, along the y-axis here, we have the change in mass for the average member of the society. The first thing I want you to know is that our spiders overall were not gaining that much mass. However, the one situation where we detected a decrease, a significant decrease in mass, was when you had misinformation in the hands of a Keystone individual. So if you have misinformation in the hands of your most socially influential members of your society, it causes a decrease in your mass gain. You can look at these animals and look at their abdomens and see that they've actually shriveled up. They're like little raisins, right? So misinformation in the hands of your key individual can cause your society to literally wither. And if I let it go on for long enough, presumably they'd start dying. So, information, I guess depressingly, only has an effect when it's bad information. So good information doesn't seem to help you at all. And bad information, yeah, that has an effect in the hands of the most socially influential individuals, and it's bad. I mean, you're probably thinking to yourself, this sounds like my work, this sounds like my government or something, right? But in fact these are just spiders. But again, these sorts of dynamics, people talk about them inside of primate societies, talk about them in human societies, but really sussing out these dynamics experimentally is just intractable for most social systems. So in summary, misinformed keystones can slow the speed with which a whole society learns about their new environment, which is bad. Misinformed keystones can reduce the collective weight gain of their society, and yet sadly, informed individuals, regardless of who they are, have no positive effects at all. And this is bad, because this means that keystone individuals could be point of susceptibility for their society, right? So if they have good information, it doesn't help you soar at all. But if they have bad information, well, it can be bad for you, right? And so why would you have these keystone individuals? Well, we know under stable conditions in laboratory, it's advantageous to have them around. But under dynamic conditions, it might be quite costly to have these socially influential members around inside of your group. So, solution. Can you just kill a keystone? Can you just determine that a keystone has become problematic, that it's incompetent, that it needs to be weeded out? Can you just murder it? Well, it turns out it's not actually that simple. Because as we just talked about a moment ago, as we sussed out theoretically and empirically in the system as well, there are legacy effects. And they can transmit this misinformation to other individuals. So even after you murder these individuals, even if you could extirpate them from the society, their negative effects persist after they're gone. Their misinformation sticks around for a long period of time. And that means that each and every day that your society endures the ill effects of a problematic keystone is yet another day that you have to pay for them even after they're gone. The double whammy, you get screwed twice by having these things around. And there you are. They told me I had to say something political or something, some social commentary. I was like, what an opportunity here. Look at that. The first time I showed this slide to somebody, I think it was in Australia, and people gasped. So, I think it was meant to be a joke then. It's not a joke anymore. So, what are the effects of keystone individuals in situ? All right, so this is a year and a half old. It becomes more and more depressing as something. All right, so when we go into the field, though, are there any long-term effects in situ? So we know under stable conditions in laboratory, it's good to have these keystone individuals around. We know that they're problematic to have around if situations are dynamic and they have misinformation. We don't actually know what happens in real life in the wild. But the prediction here is that the bolus of the most extreme group member could drive colony foraging behavior at each site in the wild. And then secondarily, that there might be site-specific selection on colony behavior, that it might be advantageous to have a more aggressive colony to have these keystones under one set of conditions, but costly elsewhere. And in particular, we test the prediction that more aggressive colonies will be favored at arid sites. Having these keystone individuals around will be advantageous at arid sites where prey is limited, but not at wet sites where enemies are abundant, or those ants and also parasitoid wasps. So for this, by the way, if you were not impressed with these last set of data, just lie to me after this talk. Just lie. All right, so for this, we have 19 shy individuals, 1 gold individual in these experimental colonies, and we deployed 30 to 35 colonies per site at 8 sites along 2 precipitation gradients. One from the Namib Desert heading north to Angola, and a second from the Kalahari Desert heading east to Lesotho. This resulted in between October and February of 2016 to 2017, I just got back a month and a half ago, I drove 24,000 miles to check on these things, which is actually approximately the circumference of planet Earth. So again, if you're not impressed, just lie. All right, so, and then we look at the number of attackers these colonies deploy in response to a staged vibratory stimulus as administered by a vibrator. And there are 4 arid sites and 4 wet sites and 2 major deserts and 2 adjacent savanna habitats. And these preliminary data are just from 2 months of survival. In the wild, I have to go back in June to go check them after 6 months and do all of this again, which will only be about 12,000 kilometers. All right, so is group success determined by the phenotype of the single most extreme member of the group at arid sites? There are a couple things I want you to get out of this. First off, that boldness. Boldness of the single boldest member of the group is along the x-axis here, so your boldest member of the group is actually not all that bold, to a situation where the boldest member of the group is extremely bold, and the y-axis is the number of attackers that respond, the average number of attackers that respond in staged encounters with a vibratory device. The 4 arid sites are depicted here, but it's not really important that you differentiate among them. I don't really want you to pay attention to those. I want you to look at whether or not these dots are filled in, which means that the colony lived for the duration of 2 months, or whether or not they're open circles, which means that that colony winked out, it went extinct, everybody died, nobody escaped, death, right? And we can see the carcasses of the spiders inside. 2 things I want you to get out of this figure. 1, yes, the boldest of that single boldest member of the group is positively associated with the success of the entire society. And 2, there's positive selection on colony aggressiveness at that site. The colonies that survived fell in the upper portion of this distribution. So at arid sites, these key individuals, these extremely bold individuals, have a large social influence in the collective behavior of the society. And it's advantageous, right? It's good to have these things around because they're facilitating the persistence of your society in the wild and your ability to produce egg cases and make offspring societies. So that makes us feel good. For wet sites, there are a couple of things here. So again, closed circles are colonies that survive, open circles are the colonies that died. All the various wet sites towards Angola and Lesotho are depicted in these various cool colors. 2 things I want you to get out of this. 1, there is no significant relationship between the boldness of the single boldest member of the group and the collective behavior at these societies. That is a flat line. Squint at it all you want. So at these sites, these bold individuals, they don't appear to have any social influence at all. You can have them all day long. Nothing happens, right? So there are stable differences across colonies in their collective aggressiveness, but it has nothing to do with these extreme phenotyped individuals. So extreme phenotyped individuals only appear to be socially influential at some sites, but not others, which means that the rules that dictate collective behavior might be different across these sites, and nothing like this has ever been demonstrated. And then secondarily, there is no positive or negative selection on colony aggressiveness. So there's no cost or benefit to having these individuals around. So, bold individuals appear to be socially influential at arid sites, and they're actually advantageous. And that makes sense. They should have social influence at sites where they're advantageous, right? But then they appear to have no social influence at these other sites. But why, right? What's going on there? I mean, it's not costly. So, we're having a philosophical pause here for a moment. What actually makes a leader? Well, myself, in fact, most papers that have ever been published on animal leadership tend to focus on the traits of these charismatic, highly extreme phenotyped individuals and marvel at them. What is it about these individuals that makes them so socially influential? But there's actually another phenomenon that needs to be explained, and that is, what is wrong with all these other people? Right? Why are they socially susceptible? What is going on with them? And they're actually the more populous phenotype, right? They're the ones that drive the pattern, right? So the question is, are these key individuals, these movement leaders and sticklebacks and pigeons, or heads of war parties and chimpanzees, human social political figures, or matriarchs and elephant societies, are these individuals socially influential because of their traits? Or is it the social susceptibility of everybody else that needs to be explained? And because we have sites where key individuals, where bold individuals appear to be socially influential, and sites where they aren't, this allows us to suss out this question directly by making chimeric colonies. So for these colonies, we have 19 shy individuals and 1 bold individual, and we mix individuals from across sites. We either have bold individuals from arid sites where they have so much social influence, paired with shy individuals from wet sites where they're not following anybody. And we pair bold individuals from wet sites where they have no social influence, and we pair them with shy individuals from arid sites where they are used to following bold members of their species. So the question is it all driven by key individuals, these bold individuals, or is it all social susceptibility? And then we assay colonies' behavior in terms of the number of attackers that respond to prey. And we only have this performed along 1 precipitation gradient here. We have a second one that we're doing starting about a week and a half when I start teaching animal behavior. My lab actually is doing independent studies on these animals, and one of them will be making chimeric colonies in Namibia. All right, so what happens here? Is it social influence or is it social susceptibility? So can bold spiders from arid sites affect shy individuals from wet sites? Can these bold keystone individuals from arid sites catalyze behavior in these shy individuals from wet sites? No. Doesn't matter how bold these key individuals are, there's no effect. There's no effect on the collective behavior of the group. So taking these socially influential individuals from an arid site does nothing when they're in the context of shy individuals from wet sites. Will shy individuals from arid sites, though, where they're used to following these bold individuals, will they follow a bold member of their species from a different population where they normally don't have a social influence? The answer is yes. So if you compare these shy individuals from arid sites that are used to following bold conspecifics, it doesn't matter whether the bold conspecific comes from their population or another population half a continent away. They'll follow anyone, right? So it's not this social influence of these bold individuals at all that's driving the dynamics of the system. It appears to be the social susceptibility of everybody else. They'll follow anyone. And what this does is it draws into question basically the interpretability of every single paper ever published on animal leadership, which transfixes on these key individuals, these ones that when you add or remove them, everything changes. And long ago, maybe about 20 or 30 years ago, there was a revolution. The revolutionary idea inside of sexual selection was that females might be more than passive receptacles, and that they might have some involvement in the sexual selection process. And this changed the dialogue of sexual selection for a long period of time. I think that to the same degree, we could have a much smaller, I'm not saying at the same level, a diet Coke version where we sort of consider the social susceptibility of these other members of these populations. And it might not be the attributes of these key group members at all that's driving the dynamic. So what about a control? So there's another social spider in southern Africa, Stegodicus memisarum, which is independently evolved sociality and occurs on the opposite end of the genus's phylogeny. And these individuals also differ in their boldness. So will these shy individuals from arid sites follow a bold heterospecific that has independently evolved sociality and shares no evolutionary history in a social context? Will they follow a different species? Yeah, they'll do that too. A bold member of a different species is enough to catalyze a shift in the collective behavior of the group, which means it's really a social susceptibility that's driving the whole dynamic. And for the wet sites, we have to show the wet sites, presto changeo, those numbers aren't going up, and that is actually significantly going down. It's one site, I'm not going to interpret that, I'm not going to do any arm waving, the data are cool enough as they are. In fact, it is social susceptibility and not the phenotypes of these key group members. So, yeah, is it actually social susceptibility? That's the trait that needs to be explained. We don't know whether it's local adaptation and social susceptibility. We don't know whether it's plasticity. Maybe if you just starve a population for long enough, you make them in poor enough condition, they'll follow anyone. Could be. Who knows? But it is an intriguing line of inquiry that's never been explored before. And so I guess I'll sort of leave you with the notion that in a population of these spiders, or perhaps in any animal, without a socially susceptible population, there can't be any leader individuals. There can't be keystone individuals. But in the hands of a truly socially susceptible population, anything, even coarsely approximating the right phenotype, will do. And so I sort of find myself in sort of an Escher moment here, a philosophical pause at the end of my talk where, are keystone individuals really keystones then? Maybe they are, because if you add and remove to the groups, everything changes. But to some degree, they're also not. It's actually these quiet, more populous phenotypes that are probably the culprits, the drivers of the dynamic. And if you actually want to take some sort of like philosophical advice from some spider biology, maybe the next time that you think about leaders inside of your own societies and what drove them into their situations, maybe actually it isn't some sort of endogenous attributes about those individuals, but in fact you and perhaps everybody should warp the black mirror a little bit and take a ponder within and blame yourself a little bit. And with that, I'd like to thank Noah Pinterwoman, who's really the brains behind this operation. She's at UCLA, and she helps reel me in whenever I'm being hysterical in response to viewers. My graduate students, Colin Wright and James Lichtenstein, and my former graduate student, Carl Kaiser, Nick Kaiser, is actually here today, just back there, for going around in the Kalahari Namib deserts and driving tens of thousands of kilometers, listening to crappy 1980s pop music. My postdoc, Andreas Modelmeyer, funding from the My National Science Foundation with Israel, the National Science Foundation, ILS and DEB, and the National Institute of Health, who just gave us an R1, so I'm totally shocked and very, very thankful for that. And also, I'd like to thank student collaborators, consultants, and friends here and all over the world that remind me that science is a dialogue, and thankfully, I'm not in it alone, thankfully. And thank you very much for listening.
have you thought about looking or look at all to see if there's a certain percent of the population that has to be passive followers, or do you see this?
To tighter it out, like what proportion needs to be these shy individuals? I have a lot of tightening experiments that I have in mind. So you should know about between 5 and 15% of individuals inside of societies are bold, but it seems to be whoever the boldest member of the group is, that's the major determinant of collective behavior in society. So it's someone that's slightly bolder than everybody else and seem to have so much social influence. We have no idea about what proportion of society needs to be shy in order to see these dynamics, although it would be quite interesting to us. One of the other questions is if shy individuals in the group have conflicting information with the Keystone, what happens? So, the Keystone might have misinformation, but if other shy generic Joe Schmoes have conflicting information, how many of them need to have conflicting information before you see the social influence of the Keystone overturned? Or how does that change the rate at which the whole society learns about the novel environment? I love to do those studies. And if you actually know of anybody who has a master's or an undergraduate degree that's interested in animal behavior and wants to join a lab, I have money and space, and I will take them to Africa, they can wander around, and I would love to address those questions. I have one graduate student working on something like that right now. It turns out if everybody has different information in the Keystone, no one pays attention to the Keystone. But at what point, when's the tipping point? We don't know. Right here.
Is an individual always born to be a Keystone shy, or can they change their behavior? For example, if the Keystone is ill, can someone become one?
Yeah. All right. So there's a few things here. One is it additive genetic differences that underlie differences in personality in these individuals? Unlikely. The relatedness coefficients like 0.9, down to 0.74, but normally above 0.9 in this species. So it doesn't appear to be genetic differences among individuals that underlie these differences in personality, although they are quite stable once individuals are mature. I would predict that there are environmental influences early on in life that cause these differences. Also, there's an effect of social stability. So if you leave a specific set of individuals, all shy individuals together in a box, and you leave them for about 6 weeks, one or two of them will become bolder over time. And the longer that those individuals are together, the more unlike they begin to behave. So some individuals bifurcate out of personality space and become quite consistent. However, if you take individuals apart and you put them with new individuals all the time, that never happens. If you take individuals apart and put them right back together, the exact same individuals, controlling for physical disturbance, the same phenomenon transpires. So something about social stability actually causes this bifurcation where a very small proportion of individuals become extremely bold. And I didn't have time to go into it, but these legacy effects, I actually think we know what's going on here. So these bold individuals, these extreme type of individuals, actually catalyze some of these other shy individuals in the society to become bolder and bolder over time. It's not as stable as these Keystone individuals' phenotypes, but after you remove the Keystone, we think they've prepared an almost Keystone that's almost as bold as them to sort of assume the role. We think about the experiment like taking one of those individuals out, starting a new society, and seeing if they can have the same level of effect that these long-term bold individuals have. But we haven't done those yet. But I suspect that would work. And so that they sort of almost train or catalyze an almost Keystone that can assume their role. Way back yonder.
How does the relatedness of the entire colony affect their response to the Keystone individual?
Oh yeah. So we have control. So like the slope of those relationships between the number of attackers and the boldness of the single boldest member of the group don't differ when societies are composed of unrelated individuals or related individuals. But we don't know. That's just one metric. Someone has showed in a conjurer that groups composed of related individuals are more efficient at prey extraction, so they're more effective at turning prey mass into collective mass gain. The mechanism is totally unknown, but at least under some circumstances, they appear to be able to suss out kin versus non-kin. For almost all of our experiments, we don't mix individuals across groups because reviewers will become very angry with us if we compromise the relatedness of group constituents. So we take one giant colony and make lots of sub-colonies because we know the relatedness, pairwise relatedness coefficient is not highly variable within the parental colony and quite high, reliably so. So it could affect lots of things, but we tend to avoid that unless we're making chimeric colonies, and then we have no choice. Right back yellow.
What determines the sex of these social spiders, and how do you explain the super biased sex ratio?
Yeah, that is also a mystery. All right, so for sex determination, females have 2 extra sex chromosomes over males. So males have X1, X2, and females have X1, X1, X2, X2. So female eggs always contain 1 X1 and 1 X2, and male sperm either have X1, X2 or not. They either have both sex chromosomes or neither. And then if you look at the male sperm, though, they have equal sex ratios. So the ejaculate being stored in the female's reproductive tract has an equal sex ratio of males to female sperm or conferring sperm. But if you allow the fusion event to happen and crush the zygotes immediately as soon as they're fertilized, as they're coming out of the female, you'll see that there's already a female by sex ratio. So somewhere between the representation in the sperm and the fertilization event, the female by sex ratio transpires. We've actually recently shown that there's variation among populations of one transitionally social species in primary sex ratio that's associated with colony extinction events. And sites that have more colony extinctions tend to have higher female by sex ratios, which is consistent with some old Caldwell papers. Right here.
You said your spiders were essentially blind?
Yeah, they're not, and they can see light and dark, and they can see maybe a few millimeters in front of their face.
Do they communicate chemically or tactily?
Oh yeah, well we know seismically they can. In fact, one of the mechanisms that I think that drives is social susceptibility. I think that shy individuals from these arid populations just might be more susceptible to recruiting to the vibratory cues of conspecifics moving on the web. And so they just feel the vibratory cues of other individuals out there, and they're more likely to respond to that. So I think that's the proximate mechanism that underlies social susceptibility here. But seismically, we know they do that. There's recruitment behavior, so they're like, it's like the 1950s and 60s now. No one's explored this recently, but individuals will go out on the web, and some individuals pull on the strands of the web, and that recruits other members over from the group. So there appear to be recruitment seismic cues as well. Chemical cues, no one knows. But we do know that there are differences in particular hydrocarbon profiles across colonies, so there's at least some potential for something there. And there's variation within colonies, but no one really knows. But these things could be spewing out volatiles, and we would have no idea. The sensory ecology is not really tacked down very well. Although in an age of laser Doppler vibrometers and vibratory communication and solitary spiders being worked out quite well, I think that it's possible now more than ever to be able to intercept their communication if it's seismic and pretend to be a social spider on the web, to be able to mimic their vibratory cues of a prey or of a conspecific moving on the web and detect what these other individuals are doing. So, mostly seismic, we know that, but everything else, who knows? And then maybe one last question. I'll try to make it brief. Right down. Yep, you got it. You.
Yeah. So Ian Cousin's done some really beautiful work on collective behavior and the sort of effective leadership through small numbers.
Yeah.
So if you have this bold individual, is it positioned someplace where it has access to the best information in the tree?
Yeah. So we sort of operate on the assumption here that when it's the first one moving out into the environment, wandering around, it's acquiring information then. But it also, we don't know about what's transpiring inside of the nest. The nest, so Alex, do you know Alex Jordan, who's a group leader with Ian Cousin and Rob Sal right now? No. So I was supposed to be sending him a bunch of these colonies to go suss this out. You should know, Ian likes this work, but he doesn't want to call it personality. But you know, we do have an intended collaboration for next year to try to figure out what's transpiring inside of the nest, and to try to figure out whether the network of interactions and movement behavior that's transpiring on the web is somehow different when these keystones are here or not, when they vary in their degree of boldness. But no, it's quite possible that these bold individuals could be tap dancing on the inside of these colonies. We have no idea at all. It's hard to see the interior of the nest, and even imaging techniques have been not that helpful. So thanks again for having me, everybody.